In this video, we're going to learn how we can use the bond energy to determine the heat of a reaction. Bond energy is the amount of energy required to break a bond, and it's the measure of strength of a chemical bond. So the larger the bond energy, the stronger the bond. So in this example, we have hydrogen gas being broken into two hydrogen atoms, and the heat of that reaction is 436 kilojoules per mole, and it's an endothermic reaction. So a couple things to keep in mind. The process of breaking bonds in a molecule is always endothermic. Energy needs to be put in to break the bond, and the formation of bonds in a gas phase is always exothermic, so it releases energy. This will help us figure out the average bond energy of a chemical reaction, knowing that breaking the bonds is endothermic and forming bonds is exothermic. So if we recap and go back to look at bond length, remember, as you move down a group, the atomic radius increases. And this means that the bond length will increase and the bond strength will decrease. So the longer the bond length, the lower the bond strength. So in this example, we have the hydrogen fluoride. The bond between them, the length is 92 picometers, and its bond energy is 567 kilojoules per mole. That's how much energy it would take to break the bonds. Between hydrogen and chlorine, moving down one in the halogens, it's 128 as the bond length. And the bond energy goes down, it's 431. And then hydrogen bromide, the bond length is even longer, and the bond enthalpy is even smaller. And then finally hydrogen iodide, the bond length is the longest in that column, and the bond enthalpy is lowest as well. Now if we look at bond strength, depending on the type of bond there is, that will coincide as well. So the strength of a covalent bond coincides with its bond energy. So when you go from a single bond to a double bond to a triple bond, that's shortening the bond length, and that's because of the increasing number of electrons being shared, and that increases the bond energy. So if we look at a carbon-carbon single bond, the bond energy is 346 kilojoules per mole. A double bond is 614 kilojoules per mole, and then a triple bond is 839 kilojoules per mole. Another thing to note is the bond polarity. So the higher the electronegativity difference in a pair of bonded atoms, the higher the bond enthalpy. So the electronegativity change between hydrogen and fluorine is almost ionic, but that's why the bond enthalpy is so high. And then hydrogen to chlorine is much smaller, and then the bond enthalpy is smaller. And same with hydrogen and bromine. The bond enthalpy is low because the electronegativity change is also low. So as mentioned at the start of this video, we can use the bond energy to calculate the enthalpy of a reaction, and we calculate that by summing the bond energy of all the bonds broken and subtract the sum of the bond energy of all the bonds formed. So some things to note. The bond energies must be multiplied by both the number of that bond present and the coefficient from the balanced chemical equation. And the structures of each molecule must be drawn to determine the types of bonds present and which have been changed. So I've included a table of average bond enthalpies. We can find them in our data booklet and a variety of places. This one is taken from the IB Chemistry course companion. So it lists the bond and then the average bond enthalpy for all of them. And you can see that all of these bond enthalpies are positive because it's the energy to break the bond that's being recorded. So we're going to work through a sample problem, and we're being asked to use bond energies to determine the heat of reaction for the complete combustion of ethane. So we're going to assume that there's ample oxygen and that all of the ethane is being converted into carbon dioxide and water. So the first thing we need to do is come up with the balanced chemical equation. So we have C2H6 plus oxygen making carbon dioxide and water, so we need to balance that. So if we put a 2 to balance out the carbons and a 3 over here to make us have 6 hydrogens on this side, we add that all up. We have 7 oxygens on the product side, but 2 on the reactant side. So we're going to add a fraction here, 7/2 oxygen. And there's our balanced chemical equation. So our next step is to draw out the molecules. So we have ethane, which is drawn like this. So C2H6. And then we have oxygen. We have 7/2 of those. And then that produces carbon dioxide, so CO2. We have 2 of those, plus 3 water molecules. So there's our drawn out molecules. So our next step is to count the number of bonds and molecules that are there. So I'm just going to put our drawn out molecules here so we can count them. So we have the following. We have 1, 2, 3, 4, 5, 6 carbon hydrogen bonds. And we have 1 carbon-carbon bond there. Over here, we have 7/2 times 1 oxygen-oxygen double bond. And over here, we have 2 times 2 carbon-oxygen double bonds. And then we have 3 times 2 oxygen-hydrogen bonds. So now we need to use that to solve our equation. So first of all, we have to remember that the heat of the reaction is equal to the sum of the bond energies of the bonds broken minus the sum of the bond energies of the bonds formed. So the bonds broken would be our reactants, and then our bonds being formed would be the products. So we're going to sum up all the bond energies for the reactants and then subtract all the bond energies for the products. So we're going to solve that. So that's equal to the bond energy of carbon-carbon plus 6 times the bond energy of carbon-hydrogen plus 7/2 times the bond energy of the double bond oxygen. I'm going to sum all that together, and then we're going to subtract 4 times the bond energy of the carbonyl plus 6 times the bond energy of hydrogen and oxygen. So we're going to plug in those values. So we've got 346 if we look up the carbon-carbon. And then 6 times 414, which is the carbon-hydrogen bond, plus 7/2 times 498, which is the double-bonded oxygen. So we'll sum that together. And then we need to look at the bonds formed. So we need 4 times the carbon-oxygen double bond, which is 804, plus 6 times the hydrogen-oxygen, which is 463. And now we'll calculate that a little bit further. So that's equal to 346 plus 2,484 plus 1,743. And then we're going to subtract the sum of the bonds formed. So 3,216 plus 2,778. And that grand total is 4,058 573 minus 5,994 kilojoules per mole, and that equals negative 1,421 kilojoules per mole. And if you want to convert that to megajoules per mole, that's equal to negative 1.42 megajoules per mole. So that makes sense. A combustion reaction would be an exothermic reaction. So that explains why we have a negative answer for our heat of reaction. And that's how you calculate bond energy.